Hi and welcome to part 2 of my video playlist about the best methods to olefinate aldehydes. This presentation is about the use of metallated sulfones and silanes as carbon nucleophiles. These reagents have been used less often than phosphorus ylides, but are a potentially valuable alternative. For instance, if a certain stereo or chemoselectivity cannot be attained with Wittig reagents. Alkyl sulfones are slightly acidic and can be metallated by strong bases and then added to aldehydes. The resulting hydroxyethyl sulfones are usually stable or eliminate water to yield alpha-beta unsaturated sulfones. These can be reduced to alkenes by cleaving the carbon-sulfur bond, for instance with sodium. Electron-deficient aryl alkyl sulfones, however, can yield alkenes upon reaction with aldehydes or ketones directly, as shown here. If the sulfur-bound aryl group is sufficiently electron-poor, the initially formed alkoxide can undergo intramolecular aromatic nucleophilic substitution of sulfinate and then fragment into an alkene, a hydroxyarine, and sulfur dioxide. Most reported examples are olefinations with benzothiazolyl sulfones, but pyridyl, pyrimidinil, nitrophenyl, bis-trifluoromethylphenyl, and tetrazolyl sulfones can also be used. In order for this reaction to proceed smoothly, the arine must be sufficiently electron deficient to undergo aromatic nucleophilic substitutions readily. Accordingly, the resulting phenoxide will not be very basic and will not necessarily react with the liberated sulfur dioxide. Thus, sulfur dioxide will neutralize one equivalent of base, and two equivalents of base are usually required for this olefination to proceed to completion. Occasionally, though, good results are obtained with only one equivalent of base. Sulfones are 4 to 7 orders of magnitude less acidic than ketones and usually require strong bases to undergo condensations. Silanes are still less acidic, but as shown by the two compounds in the second row of this slide, silyl groups do enhance the acidity of alkyl groups slightly if compared to methyl or terz-butyl groups. This is a rare example of the use of potassium hydroxide for the successful olefination of an enolizable aldehyde by a sulfone. Potential side reactions include the Cannizzaro and Tischenko reactions, but substantial amounts of the alkene were obtained anyway. Here, a rather acidic benzylic sulfone was used as intermediate for the preparation of a statin. Because of its high acidity, potassium carbonate in DMSO was sufficiently basic to bring about the olefination. Most condensations or olefinations with sulfones require strong bases, such as LDA or lithium hexamethyl disilicide, as in this statin synthesis. Interestingly, the metallated sulfone did not undergo beta elimination, and mostly the trans alkene was obtained in good yield. Even alpha-fluorosulfones can be used to olefinate enolizable aldehydes, as shown here. Despite the small excess only and high volatility of acetaldehyde, a high yield of alkene was obtained. The olefination of aldehydes or ketones with silanes, the so-called Peterson olefination, is assumed to proceed either by an almost concerted 2+2 cycloaddition, like the Wittig reaction, or by intermediate formation of a deprotonated beta-hydroxysilane. Again, the precise mechanism will probably depend on the electronic and steric properties of all the reactants. Because most alkyl silanes are not acidic enough to be metallated stoichiometrically at reasonable rates, some other strategies have been explored to prepare alpha-metallated silanes. In this example, an alpha-phenylthiosilane was treated with lithium and a naphthyl radical anion, what led to a sulfur-lithium exchange. Interestingly, this metallation could be accomplished in the presence of an aldehyde. The expected olefin was obtained with high trans selectivity. In this example, an alpha-chlorosilane was converted into an organozinc reagent and then used to olefinate an aldehyde. In this instance, a high yield of cis olefin resulted. A simpler alternative for the cyanomethylation of aldehydes may be the condensation with cyanoacetic acid followed by decarboxylation, but this often yields trans alkenes and requires strong heating and may not be applicable to beta-lactams. Here are two examples of the preparation of substituted acrylates from ethyl trimethylsilyl acetate. As base, potassium trimethylsilanolate was used, and in these instances mostly trans olefins resulted. In the second example, however, where the aldehyde contained an acidic alpha proton, the yield of alkene was low. This is an example of the use of catalytic amounts of cesium fluoride to promote the addition of a silane to an aldehyde. The silane here was an imine of silylated croton aldehyde. The latter cannot be condensed directly with other aldehydes because it would undergo self-condensation and Michael additions. The imine, however, is less electrophilic than croton aldehyde and will not dimerize as readily. The first intermediate formed in this reaction was a silylated secondary alcohol. Acid-catalyzed hydrolysis of the imine and beta-elimination then yielded the observed product. Alpha-bromosilanes can be metallated by treatment with chromium-2 salts, as in this example. No strongly basic intermediates are formed during this reaction, and no significant epimerization of the starting aldehyde occurred. The initial product in this case was a hydroxyethylsilane, which could be transformed into a cis-alkene by an excess of potassium hydroxide and methanol. In this example, an imine of alpha-silylated propanal was lithiated by treatment with sec-butyllithium. The resulting intermediate added cleanly to an enantiomerically pure aldehyde, without extensive epimerization. The final alpha-beta unsaturated aldehyde was obtained by acid-catalyzed cleavage of the imine. Such condensations cannot be achieved by direct treatment with an excess of propanal and a base, because this would probably lead to epimerization and to mixtures of cis-trans isomers and secondary alcohols. Propanal would also undergo self-condensation to a large extent and yield a series of byproducts that would be difficult to remove from the target product. So, what are the potential side reactions? Although alkyl silanes show only a weak partial negative charge at carbon, treatment with very acidic aldehydes or protic solvents can cause protonolysis and cleavage of the carbon-silicon bond. In this example, reaction of alpha-silylated and lithiated butyrolactone with acetaldehyde only gave a low yield of the expected olefin, but mostly the desilylated lactone. It is, however, not clear what the precise mechanism of this reaction was. Then, if electron-deficient alkenes are the product of a given olefination reaction, some nucleophiles present in the reaction mixture can add to this newly formed alkene. It has been proposed, for instance, that the low yield obtained upon reaction of alpha-silylated butyrolactone with LDA followed by addition of acetaldehyde is due to addition of diisopropylamine to the newly formed alkene. A higher yield could indeed be achieved when lithiated triphenylmethane was used as base instead of LDA. During olefinations with metallated alkyl sulfones, one occasional side reaction is the formation of symmetric alkenes from the sulfone. Here, for instance, 17% of a symmetric stilbene was obtained as byproduct. These alkenes are probably formed by SN2 displacement of sulfinate, as shown in the lower equation. Instead of one-step olefinations, metallated sulfones can also yield alcohols or undergo condensation reactions and yield alpha-beta unsaturated sulfones. In this example, depending on the workup conditions, either an olefination product or a condensation product was obtained. The reaction of metallated sulfones or silanes with aldehydes can yield stable secondary alcohols. Olefin formation may either be carried out in a second step or be accelerated by addition of chlorotrimethylsilane or boron trifluoride etherate. Then, strongly acidic or highly enolized aldehydes may also just protonate a metallated sulfone or silane, and this can be difficult to prevent for a given pair of reactants. The best strategy is to metallate the sulfone or silane stoichiometrically with a strong base in an apolar aprotic solvent and then add the aldehyde slowly at low temperature. Then aryl sulfones with electron-deficient aryl groups, as those required for one-step olefinations, will also readily undergo nucleophilic aromatic substitution of sulfinate by strong nucleophiles. This could be the base or the metallated sulfone as in this example, or even an aldehyde enolate. On this and the next slide there are some more examples with different bases. Mostly strong bases are required for these olefinations. You can also find this reference list in the description of this video. The next presentation is about condensations of aldehydes with ketones, carboxylic acid derivatives and some further carbon nucleophiles. These condensations are by far the most relevant aldehyde olefination reactions, but do not always enable a good control of the cis-trans selectivity. So long.